Welcome to the second take of me trying to prove that the derivative of a to the x is equal to a to the x, the natural log of a. This is a tough derivative to do, and I'm only going to prove it using first principles. I'm not going to prove it using L'Hopital's, neither series expansions. I don't even think you can prove it using series expansions, so I'm not going to use L'Hopital's. But here is the proof. So I hope you know what first principles or the definition of the derivative is. It's basically f of x is equal to f prime of x is equal to f of x plus uh, delta x minus f of x over delta x, and this is as delta x approaches 0, right? The limit as delta x approaches 0. So let's say f of x is a of x. So now we have f of x is equal to a to the x. So now f prime of x is equal to a to the x. Limit, I got it right, limit. Alright, limit as delta x approaches 0 of a to the x plus delta x minus a to the x over delta x. And a to the x can factor out, so that's equal to a to the x limit as delta x approaches 0. The reason why a to the x can factor out because it has nothing to, first of all, it can factor out in the fraction, and second of all, it doesn't have anything to do with delta x, so it's just a constant basically. So that's a to delta x minus 1 over delta x, and that is our first part done, right? That's the easy part done. Now we're gonna have a kind of a philosophical thought about functions. So if you guys think about functions, you've been doing it through your whole life, adding, subtracting, multiplying, dividing. They're all functions, right? They're just the square root is a function. That's why there's an f of x equal to square root of x, right? Fx it's a function, right? And everything that has a one output for an input, that's a function. Depends on how many outputs you have. So for example, f of x y of x plus y is equal to, well, whatever the heck you want to make it, you know. So we have to treat this as a function, right? A to x we have a function, and this we have another function, right? You forget, just try to forget everything you've learned about limits, because you cannot evaluate this limit. So we have to go to a completely different realm evaluating this limit. Let's say this is L of a, right? It's a function of a because we can't manipulate delta x because that'll make it a little bit messy, right? So ATX L of a, and that's equal to let's make it a little bit more clear. So the derivative of ATX is equal to ATX L of a, and that's it. That's all. That's all. So what's L of a? What is L of a? What do we want to find what del L of a is, right? So first of all, before we find what L of a is, let me show you something, right? I'm going to show the graph of 2 to the x and 4 to the x. So let's show you the graph of those. Right now, let's say that's like that, and I'm sorry it's a little bit turned because I'm a little bit turned as well. There you go. Oh, sorry, that's not the graph of 4 to the x. They're more like that. Okay, so we have those graphs. Let me turn this graph a little bit. Unless if they want to do that, then yeah. Okay, so you can verify these points, but I'm going to take the point 0, 1, and 1, 2 from both graphs, right? So our slope is equal to 1 because you can do it yourself. That's 1, right? And we're gonna take some points of 40x. We want our slope to be 1 as well, and you guys can try to find points, but the 2 points that work for me, that equals to the slope of 1 with the secant line that's equal to the slope of 1 is negative 1/2, 1/2, and this is at 0, 1 as well, right? 0, 1. So the slope is equal to 1/2 minus 1 over negative 1/2 minus 0, which is equal to 1. It's negative 1/2 over negative 1/2, which is 1. So there's some implications that this explains. So basically, we're saying that the average slope, we're saying that these are exponential functions. So intuitively, geometrically, they are increasing fast. So the slope is increasing pretty fast as well. So we're saying that this blue area has average slope 1, right? Blue area has average slope 1, but the slope only increase. So some point in that blue area, some point in that blue area has to have a instantaneous slope of 1, right? Seems kind of intuitive, but it actually follows a theorem called the mean value theorem. If you want to read on that, that's pretty cool. But the blue area has average slope 1, and so some point in there has to have a slope 1, right? That means some point, because the function's increasing continuously, exactly at 0, the slope has to be less than 1, right? So 2 to the 2tx L of 2, so d dx of 2tx L of 2 at x equals 0, I'm going to use this notation, is smaller than 1, right? And it's the opposite for this, right? The red area right here means the average slope is 1. So there has to be a slope of 1 before it reaches 0. Before the function reaches 0, there has to be a slope of 1, right? So, and the function's increasing, so we have our slope at 0, x equals 0, to be greater than 1. It's greater than 1. So, there exists an a in between 2 and 4 that this fact is exactly equal to 1, right? And we gotta find, it's our mission to find that, right? It's our mission to find that. No, it's not our mission to find that. It's math, so we can define anything we want, and we are going to define this new number as e, right? We are going to define this new number as e. So m of e is equal to 1. We're going to define this new number as at which d dx of e to the x, m of e at x equals 0 is 1, right? And e to the x at, yeah, well, no, this is not d over dx. This is not d over dx. I'm sorry. D over dx 2 to the x, right? Like d over dx 2 to the x equals to 2tx L and L of 2, right? And I'm not supposed to use m. I'm supposed to use L. I'm sorry. So L of e at x equals 0 is equal to 1. Well, we already have x equals 0. X equals 0 is right there. So e to the 0, e to the 0 is 1. So we will just leave it as L of e is equal to 1, right? So L of e is equal to 1. And if you guys are kind of smart, you'll know what function does this. But there are many other functions that do this, so you can't just rely on that one function. However, we are going to prove stuff now. We are going to say f of x is equal to 2. Now we're going to say f of x equal to a to the x. This is the proper proof now. So if we have ourselves f of x equal to a to the x, then our derivative is going to be a to the x L of a, right? A to the x L of a. Now, we want to scale this by some factor. We want the nice e. We do want the nice e, because if we have the nice e, we'll have it so that L of e is equal to 1, and then we can eliminate the L of e and we can work out the stuff, and it'll be great, right? So we're gonna scale a by a certain exponent. No, this is this is now a function. It's still f of a is equal to it's still f of x is equal to a to x. I'm sorry. So we're gonna scale x by k. Now we have a to the kx is equal to a to the kx, right? And a to the kx is also equal to a to the k to the x, and we want this a to the k to be e. We want a to the k to be e, and that's equal to that's equal to 1, right? And from this definition, we could really should just put derivative e dx equal to e dx, but it's not a proof yet, right? No, we don't want this to be equal to 1. This is equal to let's say a to the k is equal to b, a number b, where b equals e, and this is want. B equals e, and this is want, right? So that's btx, right? So now what if you take the derivative of it? If you take the derivative of this, I hope you know the chain rule. The derivative of this is just equal to k f prime of k to the x, right? K f prime of k to the x. And obviously we want our slope as x equals to 0. So if we have this at x equals to 0, so let's put this at x equals to 0. This is at x equals 0. We'll have ourselves k f prime of 0. K f prime of 0, right? And I've already told you that f prime of 0 is equal to a f prime of x equal to axla. So that's equal to k f k a to the 0 l of 0, k a to the 0 l of 0, which is equal to just k l of 0, right? It's just equal to k l of 0. And we want this to be equal to 1, right? This has to be equal to 1. So if b equal to e, then k l of 0 has to equal to 1, right? Because we have our b as a to the k. We want b to be a to the k, right? And this is what happens when you differentiate a to the k, or when you differentiate f of x, a to the kx, right? So if you have any questions, just ask me in the comments, because this is really hard to understand intuitively. I'm trying to make it as easy as possible. So we want this to be equal to 1. So let's solve for k, right? We want to figure out what this k is that turns it into e. It'll be 1 over L of 0. No, this is not L of 0. I'm sorry. This is L of A. L of A. L of A. L of A. So we have 1 over L of A is equal to k, right? So now let's do it. Let's solve the equation that we really wanted. Let's solve the equation that we want in order to find out e, right? So we have now we have our a to the power of 1 over L of A to the power of k is equal to a is equal to the wait, no, this is k, so we already found out k to the power of x is equal to e to the x, right? And our ultimate mission is basically to find out what L of A is, right? So let's take the natural log. You guys have learned natural log already, I hope. So that's x is equal to, well, this is the same thing as x over L of A. So and the natural log rule states that we can just yeet the thing out of its function. So we have x over L of A times the natural log of A is equal to x, right? Starting to get pretty interesting. We can multiply by L of A both sides. If we multiply by L of A both sides, this is what you're going to get. You're going to get x ln of A is equal to x L of A. And boom, you found the function. This is what L of A is. That is what L of A is, right? L of A has to equal ln of A in order for the function a to the kx to become e to the x. So the slope at 0 is equal to 1. Right? Amazing. This is an amazing discovery that I just found literally two hours ago. I found this. No, I can't even say I found this discovery with a lot of help from. Gotta give a shout out to MIT and David Jerrison. He's amazing, professor. He does make things overcomplicated. That's why it took me a while to figure this out. But L of A is equal to ln of A. So now we can beg the question. What is L of A? It's equal to ln of A. And what is the derivative of A to the x? Derivative of A to the x is A to the x L of A, which is equal to A to the x ln of A. And that is my mic drop right there. That is amazing. And we can check this for e to the x as well. Let's check it for e to the x to see if it works, right? E to the x, no, d dx of e to the x is equal to e to the x L of e, and we already established that this is equal to e to the x times 1, which is e to the x, right? But this is also equal to e to the x ln of e, which is equal to e to the x times 1, which is equal to e to the x, right? So our L of e, we found our L of a, right? So if you go back to this, the limit as delta x approaches 0 of delta x minus 1 over delta x is equal to ln of a. And that's going to be it for today's proof. That was really fun to make. I want to do more proofs like this in the future. Maybe with multivariable calculus though, because I've already done the single variable calculus. So that's gonna be it. If you liked it, press the like button. I might be teaching a calculus series. I will definitely feature this. And if you want more, then just hit the like button down below and have a nice day. School's tomorrow, so there will probably be a lot less videos coming. So I hope that you can understand the proof of A to the x right now. If you don't have any questions, just ask them down in the comments. I will be keen to answer them. And I'll see you next time.